I'm Tim Adamo. I'm going to be telling you about some work in progress with Lionel Mason and Atul Sharma, both of whom I think are in the crowd, but also which builds on some work I've done recently with Anton Ilderton. Okay, so just to get us all started off on the same page, I'd like to remind us of something that we've seen multiple times already this week, which is that when it comes to graviton scattering in Minkowski space, at tree level, we know everything. And by that I mean we have formulae for the complete tree level S matrix of gravity perturbatively around Minkowski space. So here I've written in a suitably opaque form the Kachazo-He-Yuan CHY formula for the endpoint tree level graviton amplitude. It's not terribly important that you understand all of the ingredients here. Probably most of us are familiar with them in one way or the other. But the point is more just to marvel that such a formula exists. But in fact, before this formula was written down, there was another formula written down in 4 dimensions, which was refined by NMHV degree. And this is called the Kachazo-Skinner formula. And it also takes a sort of remarkably compact form. There's some moduli integral. And then there's a kind of chiral splitting where the sort of self-dual degrees of freedom or positive helicity degrees of freedom of the gravitons that are being scattered are bundled into a determinant, and the negative helicity or anti-self-dual degrees of freedom are sort of bundled into another determinant. And if you sort of restrict the Kachazo, the CHY formula to 4D kinematics, it's been shown that in some sense you can recover this Kachazo-Skinner formula. Okay, so the point is just that at tree level in Minkowski space, we know all the graviton scattering amplitudes in these guises, if you like. Now, the question I'd like to talk about today is, what about graviton scattering in a curved spacetime? And so we've heard a bit about this already this week in the setting of ADS or DS. But the point I'd like to hammer home is that ignoring certain exceptions in very low dimensions, we know very little, even in very simple curved spacetimes. So for graviton scattering, at least in plane wave spacetimes, as far as I know, at least at the beginning of this year, the state of the art was 3 points. So that's just evaluating a cubic vertex, right in a plane wave background. Similarly for PP waves, and in ADS, as far as I know, although maybe someone can contradict me later, the state of the art is 5 points, and that's for a very specific R symmetry sector, part of the graviton multiplet. Which in some sense you're computing using CFT techniques anyway. So the point to take away is that there seems to be a really big knowledge gap between what we know at tree level in Minkowski space and what we know at tree level in even the simplest curved spacetimes. And that could just be because scattering in curved spacetimes is really hard, and we could just give up hope and think that, well, there's no way to get these kind of all multiplicity results that we know and love in Minkowski space in curved spacetimes. But what I'd like to tell you about today is some case where it seems that we can, in fact, get all multiplicity results for graviton scattering. And the particular kind of spacetimes I'd like to consider are plane waves or gravitational wave spacetimes. And like I've sort of already indicated, from some sort of naive perspective, this seems really hard. I mean, even if you weren't an amplitudes person, you're just thinking about things in terms of the background field Einstein-Hilbert-Lagrangian. This is just a monster that you'd never want to compute anything with. But even if you were an amplitudes person and you knew that the Lagrangians were not something you wanted to think about, these backgrounds seem really difficult to work with because they have functional degrees of freedom. So the plane wave or the gravitational wave, if you like, is specified by some free functions of light front time. So in a sense, this is a much more complicated problem than scattering or the analogs of scattering in DS or ADS. These free functions are going to obstruct momentum conservation, in particular in the light front direction that the wave propagates in. And there's all sorts of other kind of funky features that we don't run into in scattering amplitudes in flat backgrounds. So there's no Huygens principle for gravitational perturbations in a gravitational wave. And what that means is that the gravitons, they don't just scatter off each other, they also scatter off the wave itself. And this will lead to what are called tail terms, which are explicit new terms that appear in the amplitudes. There's no analog of them in flat space. And there's also something called the memory effect, which is that even though a gravitational wave is sort of an asymptotically flat object, if you take something that looks like e to the I k dot x at scry minus and you throw it into a gravitational wave, it doesn't look like e to the I k dot x when it comes out. So somehow the perturbations, even when they run away to the asymptotically flat region, they remember the fact that they've passed through a radiation field. So in particular, this seems like a really hard problem, certainly not one that you might expect to get arbitrary multiplicity results for. But in fact, there are also some reasons to be optimistic. So in particular, a lot of the tools in our tool chest from scattering amplitudes in a flat background in Minkowski space actually carry over to this setting in a gravitational wave. So in particular, it's known how to construct explicit graviton wave functions in a momentum eigenstate basis. It goes back to work of Richard Ward and Lionel. And also you can construct the Feynman rules explicitly. You can write down explicit representations of the graviton propagator. And also some of our, not some, but definitely not all of our favorite on-shell techniques that we all, at least in the amplitudes community, know and love also still work in these plane wave spacetimes. So in particular, spinor helicity formalism still works as a way to describe graviton perturbations in a plane wave background. And in fact, you can consider further simplifications to the background rather than just a generic gravitational wave. So that's what we're going to do today. We're going to consider not just a generic plane wave, but we're going to go to 4 dimensions and we're going to consider a special class of plane waves, which are self-dual. And intuitively, you should think of this as a gravitational wave that's composed entirely out of positive helicity gravitons. So there's one functional degree of freedom. The metric in Einstein-Rosen coordinates or in a particular coordinate chart looks like this. You have kind of this one non-trivial term written in light front coordinates, and you have this free function of light front time x minus. That function can be whatever you like, and this metric will be Ricci flat, so it will solve the vacuum Einstein equations. Because we're in 4D, there's kind of a nifty spinor description of this metric where we use a spinor dyad, omicron and iota, which are normalized so that their contraction is 1. Not terribly important that you remember that, but anyway, okay, so these are the spacetimes we want to consider scattering on. And okay, they have lots of nice properties. They have a covariantly constant null killing vector, which is just the vector iota twiddle. So it's null, so in particular, it can be decomposed in spinors. They're vacuum flat, so their Ricci tensor vanishes, and half of their Weyl curvature vanishes. So the only non-trivial part of the Weyl curvature tensor is the self-dual part, and this is proportional to 2 derivatives of this free function f, and then kind of points, if you like, strictly in the iota twiddle direction. You can write down a holomorphic frame for the self-dual spin bundle explicitly, and whenever the twice differentiated free function is compactly supported in x minus, it means that there's a well-defined S matrix for these spacetimes. And what that compact support criteria really means is that the gravitational wave switches on and switches off at finite light front time. So there's well-defined asymptotically flat regions where you can throw things in and things can come out, and you can talk about something like an S matrix. Okay, but more than that, the on-shell kinematics of gravitons or gravitational perturbations in these self-dual plane wave backgrounds, they have this cute property that they themselves are chiral. So in particular, if you consider a graviton that you throw in from scry minus with some on-shell momentum, k alpha alpha dot, that can be decomposed in spinors as we usually do, because it's something that's in the asymptotically flat region, hasn't crossed the radiation field yet, then your graviton wave function has some polarization tensor, which can be decomposed into positive and negative helicity parts, and then some e to the I phi sub k, where this phi sub k is a solution to the Hamilton-Jacobi equations on the self-dual plane wave background. So if we were in Minkowski space, that would just be k dot x. So that's this first term here. But because we're not in Minkowski space, we pick up some kind of non-trivial correction that depends on the wave profile, that function f. But you can show that things that are built out of these e to the I phi sub k's, they'll solve the linearized Einstein equations. And the on-shell momentum, as your graviton traverses the plane wave, it gets dressed by the background. So it picks up some light front dependence, but crucially, only the dotted spinor part picks up, notices the background, if you like. And that's because the background itself is chiral. And you can be very explicit about what that dressing is. So as your graviton moves through the self-dual plane wave spacetime, its momentum is given at any light front time by this expression here. And then that in turn allows you to give explicit expressions for the graviton polarization. So in particular, in working in light front de Donder gauge, which is possible because of the underlying symmetry of the metric, the negative helicity graviton polarization looks exactly the same as it would look in Minkowski space. There's nothing particularly new or interesting. This is just a particular gauge choice of our usual kind of spinor helicity representation of negative helicity gravitons. But the positive helicity one gets dressed. So in particular, you pick up the dressing of the usual dotted momentum spinners, but also you pick up a term that depends explicitly on a derivative of the wave profile. And this is a very explicit example of these tail terms that I mentioned earlier. So a negative helicity graviton, its polarization as it moves through a self-dual plane wave, nothing happens. It kind of, at least from the polarization's point of view, it can't even tell that it's crossing a gravitational wave. But the positive helicity guy, he can definitely tell, okay? So the basic idea that I'd like to outline to you is that we're gonna use something called Twistor theory to trivialize, in a way, this self-dual plane wave background and encode graviton fluctuations on it. Now, Twistor theory has been brought up a few times already this week in various guises. So thankfully, I can treat it with a light touch here and ensure, assuming that you've absorbed something from the talks that have gone before me. But if not, I'll do my best to kind of convey some flavor of what's going on. But why is this the case? Why is Twistor theory a good thing to use here? Well, because it can encode the underlying integrability of the self-dual sector of Einstein equations, and because we have a world sheet theory, which is called Twistor string theory, which we can use to compute amplitudes in such backgrounds. So basically, the rest of the talk is just explaining these two points and how they lead to some concrete answer. Okay, so here's the world's quickest review of Twistor theory. So what is a Twistor space, which I'll call P curly T? Well, for my purposes, this is going to be a three-dimensional complex manifold, which looks like an integrable complex deformation of the three-dimensional complex projective space. And it also has some requirements that it contains a 4-parameter family of rational curves, so genus 0 Riemann surfaces, with a prescribed normal bundle. So this is some technical condition to ensure compatibility with, if you like, the flat space limit of Twistor theory. And there's a theorem, sometimes called the nonlinear graviton theorem, which goes back to Penrose, which tells us that there's a one-to-one correspondence between these Twistor spaces and between Ricci-flat self-dual 4 manifolds. And if this Ricci-flat condition also means that the Twistor space emits fibration over the Riemann sphere. Okay, so what does this mean in real money? It means that for a self-dual plane wave, there will be a corresponding Twistor space, and its complex structure will be a finite deformation of the flat complex structure, if you like, on CP3, or at least on an open subset of CP3. So we can write that complex structure in terms of a deformed Dolbeau operator, something we'll call nabla bar, and that's just equal to the flat Dolbeau operator plus some deformation. So this V is some vector valued 0, 1 form on the Twistor space, and it has to be integrable. So that means that it's nilpotent. And if we work in some kind of homogeneous coordinates on this Twistor space, for a self-dual plane wave, we can be very explicit about what this complex structure is. We can write V explicitly as some representative that's constructed from the wave profile of the plane wave. So if what you're seeing here kind of doesn't mean anything to you, that's fine. The takeaway is just that we know exactly how to construct the Twistor space for these self-dual plane wave spacetimes, and the complex structure is very simple. That's the takeaway. And you can also construct this fibration over CP1 explicitly, and that gives you an explicit realization of these holomorphic curves, these rational curves in Twistor space. Each one of these rational curves corresponds to a point in the self-dual plane wave manifold. Okay, so because the complex structure on these Twistor spaces is so simple, we have, it allows us to be very explicit with our encoding of gravitational fluctuations on a self-dual plane wave. So it's very easy to find explicit cohomological representatives with respect to this deformed complex structure. So in particular, we can write down explicitly Twistor representatives that correspond to positive helicity graviton fluctuations and negative helicity graviton fluctuations on the self-dual plane wave spacetime. These are given by some cohomology data on the Twistor space. And okay, so you might say that all seems very well and good, but how do you actually use this machinery to compute amplitudes? And so the first thing to do is to remind ourselves of how this story works in Minkowski space. So there, the work of Cachazo and Skinner showed us that tree-level gravitational amplitudes, they live on rational holomorphic curves in CP3, or in some open subset of CP3. And the NMHV degree of the amplitude that you're describing is related to the degree of that rational curve. So if you can write a holomorphic map, if the z's are homogeneous coordinates on the Twistor space, a holomorphic map from a Riemann sphere with homogeneous coordinates sigma to Twistor space can be written in this form. These curly z's are the moduli of that map. And then the Cachazo-Skinner formula that I wrote down on kind of the first slide, this is just given by an integral over the moduli of these maps. And then these determinants encode sort of the kinematic data of the scattering process. And then you have some Twistor wave functions. And when these Twistor wave functions are chosen to be momentum eigenstates, the key thing here is that although it looks like there's a slew of integrals lurking in this formula, in fact, there aren't any integrals at all. They're all saturated by delta functions, which are hiding in these Twistor momentum eigenstates. And so the resulting object really is a momentum space expression for the scattering amplitude. So where did that formula come from? Well, it came from some world sheet theory governing these holomorphic maps from a Riemann surface into Twistor space. And so we can supersymmetrize CP3 just to make our lives easier. Since everything's at tree level, that's really just a cosmetic simplification, nothing more. And these world sheet theories take the following form. They're sort of first order chiral theories, where this y acts as a Lagrange multiplier, if you like, enforcing the holomorphicity condition of the map. There's some super partners, so these are some world sheet fermions. And then I've written this engaged fixed form, so there's a slew of ghosts that we're just not going to worry about. The vertex operator content of the theories, you have some fixed and integrated vertex operators. There's some fermionic moduli to do with these ghosts, so there's some picture changing operators. And the point is that the tree level amplitudes are given by world sheet correlators on a genus 0 Riemann surface. So that Cachazo-Skinner formula for n external gravitons at MHV degree d-1 is given by the following world sheet correlator, where you just slam down d+2 of the fixed graviton vertex operators, the rest of them are integrated, and then you need d of these picture changing operators to saturate 0 modes. The idea for us is to deform the world sheet complex structure from the trivial one to the background coupled one, corresponding to the self-dual plane wave pulled back to the world sheet. And this leads to two important changes to the flat space story. The first is that the world sheet OPEs changed. Anytime you have OPEs between fields that have dotted spinor indices or self-dual spinor indices, these get dressed by the self-dual spin frame of the space-time background. And also you pick up a new class of vertex operators, which, if you like, encode the background field itself or perturbations of the background field itself. So you need to sum over all the different ways of putting these vertex operator insertions down. The background vertex operators themselves don't introduce any new moduli. So a priori, you could have an infinite number of them. But it turns out that that sum is truncated by non-zero mode saturation. So this is what a generic correlator in the background coupled Twistor string looks like. That sum, in fact, truncates, and you get a very explicit formula for any n. So I've written this in terms of momentum eigenstates. So this is a momentum space formula for the endpoint n to the d-1 MHV graviton amplitude in a self-dual plane wave background. So it's a bit of a complicated formula, but the main thing to notice is that one of the determinants from the Cachazo-Skinner formula doesn't change at all. And that's because of the chirality of the background. So nothing that's in this determinant has changed, but the other one changes a lot. And so what are these ingredients? You have to sum over some partitions of some of the external gravitons. You have some tail contributions, which are all proportional to derivatives of the background field profile. One of the matrices that appeared in the Cachazo-Skinner formula gets replaced by this matrix curly H. I've written some of its sample entries here. It has a kind of big block decomposition that I won't bore you with at the moment, but the point is that you have some dressed kinematics and you have some background kinematics, but we know what all the entries of this matrix are. That reduced determinant, it can also be written down explicitly. There's some Vandermonde factors, there's a Jacobian, some momentum conserving delta functions get replaced by exponential factors. But okay, so what? That looked like a bit of a mess. In the time that I have, it's not a mess that I'm particularly able to unpick for you here. But the thing I would like to emphasize is that I think it's surprising that you can find anything this explicit on a background that has functional degrees of freedom. But also the formula has some very nice properties. It has fewer residual integrals in it than what you might expect from background perturbation theory on spacetime for any helicity configuration. If you take an impulsive limit where the radiation profile of the background field is just supported on a delta function, there's further simplification. And in fact, we know how to generalize this formula from self-dual plane wave spacetimes to any self-dual radiative spacetime in 4 dimensions. So that's a spacetime that's, if you like, completely characterized by its news function at Scry. So you might say, okay, that's a kind of crazy looking formula. How do you know that it's right? And the point is that the usual toolkit that we have to prove whether formulas are right or not doesn't work in a background because usual unitarity-based checks are obstructed by the background field profile. However, our formula passes many basic consistency checks. So we've explicitly checked it against, if you like, Feynman rule computations at 3 and 4 points. So those seem like small numbers, but in background perturbation theory with the Einstein-Hilbert Lagrangian, I can assure you that those are difficult computations. And in fact, we can prove the formula in the MHV sector. So that's for degree equal 1. So that if you like, if you don't believe that formula for generic degree, we can still prove it for an infinite number of amplitudes, all the MHV amplitudes. It has the correct flat background limit. So when the wave profile goes to 0, you recover the Cachazo-Skinner formula. And it also has the correct perturbative limit. So, okay, this is meant to be a conference about double copy. Earlier this year, we found an analogous formula for gluon scattering in a self-dual plane wave gauge field. This is what it is. And so you might say, well, now surely we have all the tools to write down an explicit all multiplicity double copy for scattering amplitudes on a particular class of non-trivial background fields, in particular self-dual plane wave background fields. But actually, I'm not even sure that we have what I would consider a suitable answer to that question, even for flat background formulae. So the RSVW formulae and the Cachazo-Skinner formulae. But if Yong and Ivan are in the audience, they may disagree with me. So anyway, I think I've run out of time, so I'll stop here just with some other interesting questions that we're hoping to think about. Thanks.
Okay, so let's thank Tim. Yeah, are there any questions? Okay, Ollie, you're first.
Yeah, thank you for the very nice talk, Tim. In this all multiplicity formula, you were saying it's very few residual integrals. Now, to ask in the ambitious way, if I want to slim down even further the number of residual integrals over b, over nu, over x, which of them is most feasible, or what are the tentative bottlenecks? Okay, good. That's a great question. So, there's some number of residual integrals that you're never going to be able to get rid of. And the reason for that is that you have this background field that is a function of light front time. So if we forget about gravity for a second, you just imagine a single contact vertex in like a scalar theory. And you wanted to compute the contact amplitude. You have to integrate that over the whole space-time. You're not going to have e to the I k dot x that you can integrate out for every direction, because in the light front direction, x minus, there'll be an f of x minus somewhere that will prevent you from integrating that out and just getting a momentum conserving delta function. So it's just a general feature of background computing amplitudes in strong backgrounds that you're never going to have generically be able to get rid of all the position space integrals. So in our formula, the ones that I would say are the hardest to get rid of are the ones that I wrote as dxr. So these x moduli. The other moduli, the b and the nu, those are the moduli of one or two of the components of the map to Twistor space. And you could integrate those out, if you like, by solving some version of the scattering equations. So in some sense, you could get rid of those if you had explicit knowledge about the background field profile and the kinematics and were sufficiently computationally robust. Does that answer your question? Oh yeah, this is a very helpful answer. Okay. Thank you.
Okay, so we're running slightly over time, but maybe I could just encourage some short questions. But I guess Nima is next.
Just a quick question, Tim. I thought one way of thinking about these plane wave backgrounds is like you have a bunch of gravitons, let's say, of the same helicity, and we just boost them, right? You know, so I take some collection of gravitons and they're all moving in the same direction. So you would think that the amplitude should simplify if all the other perturbative gravitons are going in the opposite direction, because you can always boost to a frame where the huge number of gravitons that's making your background are very soft. And so you would think the amplitude should be just given by soft limits. Does any simplification happen in that case when all the when the rest of the gravitons are moving in the opposite direction as the wave? I would think, yeah, that there should be an explicit formula we can predict from amplitudes ahead of time for that.
Yeah. So you're absolutely right. I think so okay, let me give you an answer which you may not consider a satisfactory one. So one thing we can definitely do with that formula is to take the limit where the background becomes a single graviton, right? And in that case, we can show that that formula reduces to just the Kachazo-Skinner formula with an extra positive helicity graviton in it. So I think what you're talking about is doing that process kind of multiple times and in a collinear way, perhaps. So I think that's totally feasible, and the formula will simplify. And as you say, it's something that could be predicted by taking collinear and soft limits of Kachazo-Skinner for some large number, and then, yeah, I think I agree with what you're saying, yeah.
Okay, Lance?
Yeah, just a similar style question, which is how does collinear factorization and or soft factorization work? And can you use that to check your formulas?
Ooh, okay, so I think the answer is that I don't know, or that no one knows, because generally the way that factorization works in these strong backgrounds is not well understood. I mean, so in some sense there has to be some analog of factorization, right? But tree level amplitudes are no longer rational functions when you turn on these background fields that have functional degrees of freedom. So yeah, it's generically not.
I thought that stuff should happen way outside of the plane wave. The splitting of one particle into two.
Okay.
And so therefore it should have a similar factorization structure.
Okay, good.
To allow you to change the number of negative helicities probably.
Right. So I think, again, I think what you're saying is correct. The difficulty here is that because of this memory effect, even if it's happening outside of the wave, it still remembers the wave profile. So that means you may not have explicit functional dependence on the wave, but you have an integral over the functional dependence of the wave, which means that you no longer have something that's just like, things aren't just built out of e to the I k dot x or dot products of the ingoing momenta. So even in that case, even when these processes, as you say, are happening asymptotically, they still remember the fact that there was a non-trivial wave profile. That doesn't mean that you can't achieve something. It just means that I don't know what the answer is.
Okay, thanks.
No worries.